prefix code is like equivalent to binary tree where all code words are leaves. And this is very obvious once you like think about it for a minute, because see, if your code word is not a leaf, if it's an internal node in the tree, that means you can extend it further and get another code word. But that means that one of the code words is a child, like a prefix of the other, right? Here, like if B was a leaf, everything would have been good. But B is not a leaf. C is a child of B. So that means the code word for B is a prefix for the code word of C, because of the way we define things here. Is that clear? Right. So you see there is an equivalence. Basically, any prefix code is equivalent to a binary tree where you have a certain property. Right. Okay. Okay, we'll move on to the next part unless there are questions. Okay, let's talk about good prefix-free codes, right? So we now understand uniquely decodable codes, we understand prefix-free codes, we know that prefix-free codes can be represented as trees, where each of the leaves represents a code word. And I hinted to you, but not quite proved, that we will not worry about uniquely decodable codes because prefix-free codes are good enough for our purposes. Okay. So with that context, let's start about what do we mean by a good prefix-free code. So if you want to get like very formal with some, we'll do the proofs very systematically in class, but just some of the other stuff where you think we are not very rigorous. The suggested book is Cover and Thomas, Information Theory, chapter 5. So that's where, if you want to like read this in more detail, and also a bunch of very good questions in the, Cover was a professor here. Okay, so the first property is for symbols S1, S2, if probability of S1 is greater than probability of S2, then the length of the code word L, S1, should be what? More than or greater or smaller than the length for S2? Smaller, right? Yeah, we saw this in last class, also very intuitive from the definition of good. Good just means that we want to, actually I should have defined, let me define good, sorry, in the last slide, one second. Good means minimize expectation of length of the code word subject to being a prefix code, right? That's like the optimization definition of good. Okay, I will give a second if you. We will post these notes as well in case you want to take a look later. But if you want to take your own notes because you don't like my handwriting or you think it helps you learn better, please go ahead. Okay. If I had a code where L length of S1 was greater than length of S2, can I create another code which is just, I know which is strictly better than my code, right? So the question is, this is, if I have LS1 greater than LS2, what I can do is I can swap code words for S1 and S2 and minimize the expected loss, expected code length. Right, so if you gave me a bad code which has like the lengths in the opposite order of the probability, I could just swap them around until like increasing probability means decreasing code length, and I will just strictly get a better expected length. So we basically proved this property with this one line of argument. Okay, and let's talk about the second property. Good. Okay. Okay, so on the second property, I will ask you to trust us for now. We will prove it in the next lecture. But it's very useful to know this property to actually learn some of the... We will actually see an actual code today, a good prefix code shortly after this. The property is that the length of a symbol x should be roughly log base 2 1 over the probability of x. Right, so this is in a way stronger than the previous one. Right, previous one was a more qualitative sort of thing where if probability is higher, then length should be smaller. This is just saying that if your probability is p, then your length should be log base 2 1 over p. This is like the negative log likelihood term you might have seen in other places. Let's do an example. Uniform distribution, the simplest distribution. Okay, so let's say you just have A and B with half of probability. Then log base 2 1 over half is log of 2, which is 1. So what we are saying, a good code for this distribution where A and B have probability half each will have length of the code word being 1 for both A and B. So like A going to 0, B going to 1, that's a good code word under this criteria. Okay, let me keep going, give you another example. So let's do in general. If X is uniformly distributed in 1 to k, then a good code will have length of a symbol x equal to log base 2 k, roughly equal. Can somebody suggest when this can be like an exact equality? When can you have length? Yeah. So the answer is when k is a power of 2, you can exactly get log k. And we already saw this, right? This is nothing new. We saw the fixed length code in the previous class. We saw it again in this class. So that's nothing new, right? So this is just the fixed length code that we know and love. Right. But in general, like the best you can do is with fixed length code is Lx equal to the ceiling of log k. You can't quite do like, because it might not be an integer, the log, right? So already like you see some justification for this property, right? For our fixed length code, you can actually achieve it. And you also see that for the uniform distribution, it's a good code, right? In general, it need not be a good code, but for the uniform distribution, which also intuitively makes sense where like, since all of the symbols have the same probability, you want them to have the same length, the code word length, and the code word length must be this thing. Okay. Please raise hand, any questions? Let's do another example. Let's look at our favorite code that we have been looking at for a bit. The 0, 1, 0, 1, 1, 0, 1, 1, 1. You will notice that we don't have a length, we don't have a probability distribution for this at the moment. Let me define a probability distribution. 1/2, 1/4, 1/8, 1/8. Let me also create the log of 1 over px. So which will be 1, 2, 3, 3. So as you might notice, for this particular code and for this particular distribution, the length of the code word exactly matches the log 1 by probability. Right, 0, the length here is 1, the log is 1. The length for the C and D is 3, the log is 3. So, and this we will actually see, not today but tomorrow, Wednesday, that this code is the optimal code for this probability distribution. We are getting closer and closer to like making very powerful statements about codes in general, and which we'll use throughout the course. Right. Okay. For now, I think that's it I'm going to say. Just remember there are two properties where really the second property, first property. So focus on the second probability, that property that the length of your code word should be roughly equal to the log of 1 over the probability. Any questions on this? Because after this we are going to see a code construction that will actually achieve this. Okay, people say happy. Good. Okay, so we will now see Shannon code. I don't know if, I think Pulkit mentioned Shannon in the last, like the intro lecture. So Claude Shannon, he did a lot of great things. Among them, he basically invented the field of information theory, which has two big parts. One is compression, which we will learn in this class, and the other is error correction coding, which is also very, very important, used in every communication you do. So this is like one of the cases where Shannon himself created this particular code, which is a good prefix-free code according to the definition, the properties we saw. Okay. I guess I won't say it right now, but maybe like as we go through the first half of the course, if you get your hands on the 1948 paper by Shannon, which is called A Mathematical Theory of Communication, read the first part, the part that covers compression. It's very interesting, written in very simple words, not very fancy math stuff. Very, very simple words, very intuitive. Yeah, you might find it interesting. Okay, so Shannon code. So this will be a prefix code, and for symbol X, we will actually achieve the length of the code word will be log base 2 1 over probability of X. You might have been seeing this log base 2 last lecture, also this lecture as well. Does anybody know why we see this 2 all that? Why not log base 3 or natural log or log base 10 or something like that?
It's because if we're only dealing with a binary, just got one, so it's 22 bits. So.
Yeah. So the answer is we are dealing with binary because our output is binary. We are encoding everything into bits, right? In another world, if we had semiconductors that are like 3 levels or something, you could be working with log base 3. Yeah. So you see, it's a prefix code, and for any symbol X, it will achieve log 1 over p of X. So it's very good code in that regard. Okay. Okay, let's do the construction. Step 1, you compute the Lx, which is this function we just saw, the log 1 over px. In this class, if you see a log and like somewhere we forget to put the 2, just assume it's log base 2, unless like otherwise stated. For each x, okay, you compute it. Sort in sort symbols in sort of Lx1 greater than equal to Lx2 ... right, increasing order of the lengths. For each symbol x, so in the above order that we just sorted them in. It's a very, very simple, if you have done algorithms, this is a greedy algorithm. Assign leaf of the, like a prefix code is a tree, as you already saw. So you are just going to assign a tree at depth Lx without violating prefix condition. And this I think you will actually implement in the first homework. Very simple idea. What you do is you know that you know that your lengths have to be this log 1 by px thing, right? So you already compute the lengths. You sort the symbols in the order of their increasing length. Then for each symbol, let's say a symbol which has length 1. So in the tree, which leaves of length 1 are available without violating the prefix, and we'll see an example. You assign that greedily. You don't need to think too much. Next symbol, you see, okay, maybe length 3. You find a place in the tree which has length depth 3, which is not like already a child of something else, and you assign it, and you go on, and then you have a code which will work out. Let's do an example, and then if anybody has questions, we will go through the questions. I think the example will help. So A, B, C. We'll take a slightly bigger example so that it's easier. So this is X, the symbol. Px is the probability of the symbol. And let's compute L of X, which I computed at home to save us time. So 2, 2, 3, 3, 5. Okay. And then as we work through it, we will assign these code words. But when we start, we don't have anything to go with. Okay. Okay, so I have nothing initially, right? They're already sorted in the increasing length, so that's also done. So step 1 is already done. Step 2 is done. Now the first symbol you see is A. Can you suggest any code word of length 2 that I can assign without violating the prefix property? Yeah, so one answer is 0, 0. I could have done 1, 1, 1, 0, all 4. Like right now there is no code, so there is no prefix property. So just anything is fine. So let's assign 0, 0, keep things simple. Okay. So I've assigned 0, 0 to A at this point. Okay, now for B. B, I need to assign again a length 2 code word without violating the prefix property. Suggestions? 0, 1, okay. I like it. I like people are like not straying off the code that I made at home. Okay. Okay, for C, I need a length 3. What about 0, 0, 0? Is that good? Right, 0, 0, 0 is not good. It's a child of A, so it will violate the prefix property. So let me assign something. I need to go to this branch, I think. Let's just take this path, 1, 1, 1, okay. Right. When you actually implement it, what you would want to do is not to take like any random node. What you would want is like sort of go lexicographically, just makes everything easier, makes your algorithm more deterministic. But for illustration purpose, you can choose anything, it's fine. So I assigned 1, 1, 1 to C. Now to D, any suggestions for D? 1, 1, 0. But let me not do that. Let me do 1, 0, 1. Okay. So 1, 0, 1, I will do D, right? Just to show that it doesn't really matter. There are a bunch of possibilities here. Okay, last one, E. E, you need a length 5 code word. Right, okay. So let me do it. Let me take a path from here, and then here, and then here. Okay, so we got a prefix-free code. It satisfies this length condition. Everything is good. Question. Is this a good code? Do you think it's the best code I can make for this distribution? Okay, let's do a vote. How many of you think this is like the absolute best code for this distribution? You cannot beat it in any way in terms of the expected code length. How many of you think it is not the absolute best code? Okay, so I see a bunch of raised hands for not the absolute best. One of you, I guess, why do you think it's not the absolute best code for this distribution?
E could be significantly smaller than that.
Yeah. So the answer is E could be smaller, right? Like what's happening here? This is not something we like. Like you have E here. You could have placed E here without, sorry. I don't know how to undo. Let me, right, yeah. So you could have made E much smaller without affecting the prefix-free property, right? And hence you could have improved. Even C. C is not very good, right? C you could have placed here. Right. So we said that Shannon codes are good codes. So they are good in a sense that we will define in the next, they come very close to the optimal, but they are not necessarily optimal. Next Monday we will learn about the code which is optimal. And but for now, I guess we will live with what we have got, and this is the code. Okay, so now show that this construction. So if you read this construction carefully, what you will observe is step 1 is obvious, there is nothing there. Step 2 is obvious, you can always sort things. Step 3 depends on the fact that when you're trying to assign a leaf, there should be a leaf available. If there is no leaf available, then you can't assign anything, right? So actually, if you have done greedy algorithms, if you have done the minimum spanning tree or something, you always need to prove that the next greedy step is indeed possible, right? So really the thing to prove here, which we'll prove now, it's like an inductive proof. So we need to prove that this construction always works. So we need to prove a leaf at Lx depth is always available always available without violating the prefix condition. Okay. So, let me go through the proof and stop me if you have questions. If you have not done proofs before, don't worry too much, only very small part of the course hinges on this. I hope you find the proof intuitive. It's not like one of those proofs where suddenly you get the result and you have no idea what happened. It's very obvious in some ways. Okay. So proof. So if we take all the things, we take this sum. This sum is 2 power. We know that the length is log base 2 1 over p of x. If you have forgotten the properties of logs, now is a good time to refresh. Now you know that the ceiling of something is bigger than the original. Ceiling of x is bigger than or equal to x. So minus ceiling of x will be smaller than equal to x. So after 2 steps basically, you can convert this to, you can remove the ceiling function which just causes problems. And then just properties of logs, right? 2 power minus log 1 over p of x is just, this whole thing is just p of x. So this is summation p of x, and this I think all of you know. What is the sum of probabilities. 1, yes, I'm saying ones. Okay, 1, right? So let me note this down as 0.1 2 power minus Lx less than equal to 1, right? This is 1. Okay. Okay. Let's keep going. Okay, so say we assigned, so this is an inductive proof. So you say that you have already done m steps and now you will prove that the m plus 1th step is possible. So we assigned x1 to xm. So next is xm plus 1. So then we already saw above that the sum of all the probabilities is less than equal to 1. So therefore, if you add from 1 to m and then you add the next one, this is clearly smaller than the total sum. So this will be less than 1. Right. So this is like based on 1. Right, because this is a partial sum. This is only part of the total sum. This one was over all symbols in your alphabet. We are now just restricting to first m plus 1 symbols. Or, so what I will do now is the sort of the key is I will multiply both sides by 2 power Lxm plus 1 and then I will move one of the terms to the right to get minus 1. Okay. Until now it's just multiplying things, moving around things, no special logic until now. So let me move this to the next page and then we will like look at some actual logic. One second. Okay. So I will copy over the last point again. So I equal to 1 to m 2 power Lxm plus 1 minus Lxi less than equal to 2 power Lxm plus 1 minus 1. Okay. Let's call it 2. Now, this is the part where like a visual representation is much easier to interpret, right? So let's look at this. If you have a tree and you are at depth, let's say you are at depth Li. You have a node at depth Li and you have a subtree below this with total depth Lm plus 1. Okay, so first simple question. How many nodes do I have at depth L for a binary tree? 2 to the L, right? So in a binary tree at depth L, I have 2 to the L nodes. Okay. Now, if I have this node at Li and then I create a subtree, right? A tree below that node with overall depth Lm plus 1, how many nodes do I have here? How many nodes do I have here? Like, how many nodes of depth Lm plus 1 are children of a node or descendants of a node at depth Li? Yes, so let me write that down. So number of leaves at Lm plus 1 that are descendants of depth Li node are 2 to the L m plus 1 minus Li. Okay. Now let's come back to this inequality. What is it saying really, right? Each of these terms, what is it saying? So this term, this is number of descendants of the code word of xi, basically, that leaf at depth lxm plus 1. What is this term? This term is the total number of leaves at lxm plus 1. So what we are saying is, if you take all the nodes you have already added, like all the leaves you have already added, you extend each of them to depth lx plus m plus 1, you see that there is still at least one node left. And let me draw it for you. But so what we are saying, and please think about this at home as well, is so what we did was, so you assigned x1 here, you assigned x2 here, x3 here, maybe you assigned x4 here, right? You are now at x5. x5 it has a certain depth, so this is like your lx5, right? Now we are saying, let's take each of these guys, extend them to the level, right? Like this. So all of these areas are like invalid. Why? Because any node here will be a descendant of the x1 node. So x1 will be a prefix if you try to assign it here. That's not good. Similarly, any node in this area is bad, right? So for example, if x1 was 0, 0, these nodes will be like 0, 0, 1, 1, 0, 0, 0, 0, all of these guys. So these are just not allowed. These are not allowed. These are not allowed. These are not allowed. So what we are trying to eliminate all the nodes that are disallowed by the prefix free property. And what we are showing is that even after you remove every node that is illegal, like which is not allowed, you are still left with one node which is still valid. Right? Any questions on this? I will give you time to digest, I guess. This is also written up in the notes which are available on the website. Okay, yeah. So just to finish off the proof. Right. So if we just write it like this, this is the total number of leaves at lxm plus 1 depth minus summation 1 to m So this is the number of leaves not allowed because they are descended from existing code word. So what we have basically shown is that this is greater than equal to 1. So there is at least one leaf left at every step, which you can assign to your next symbol, to xm plus 1. So at depth lxm plus 1, there is at least one leaf which is left. So that is basically the proof. Yeah. So sorry if it was too much, but I guess you have to say it. In next class we'll see another proof which is very similar, so I think that will help. Yeah. And we'll put these up. Right. I think I will not have time to cover the last topic, Kraft's inequality, which we'll do next lecture. I will leave it here and answer any questions. Otherwise, thank you. Don't be scared of the proofs if you are scared, because they're only for 2 lectures. Then it's mostly algorithmic. And about it, make examples. I think that will really help. Just make some trees and see what these quantities are at various steps. Thank you.